Hi, my name is Boz Rosnan and I'd like to present joint work with David Lorenz and show you how you can define an application rather than implement it. Before we start, I'd like to play a little game with you. It's called Defined or Implemented. We're going to go over different aspects of a web application and ask whether they are defined or implemented. Let's start with a static web page, which is probably the simplest form of a web application that has only presentation. So when we want to create a static web page, do we define it or do we implement it? So from an implementation point of view, we need to think about how we transfer the content to the client and how we lay out the content of the page on the screen. Now we can go ahead and write software that does those two things, but that would be very wrong to do because software like that already exists. The first part is handled by a web server and the second by a browser. What's left for us to do is to define the content and structure of the page in form of an HTML file and the look and feel of the page by form of CSS. Another aspect, the data model. Do we define it or implement it? So from an implementation point of view, we need to think about how we persist the data that our application needs and how do we efficiently retrieve it. Now we can go ahead and write specific software that persists and retrieves the kind of information our application needs, but for most application that will be wrong to do because for most application an off-the-shelf database will do just right. So what's left for us to do is to define the schema, which includes what data entities we have and what relations they have between them. What makes it possible for us to get away with defining these aspects of web applications is the existence of platforms. A web server is an example of a platform that takes static files and serves them over the internet. A browser is a platform that takes HTML and CSS content and displays them to a user. And a database is a platform that takes data that corresponds to a schema and allows storage and retrieval. Why do we use platforms? The advantage of using platforms is basically because they're already there. So we don't need to implement those aspects again. Moreover, many platforms today are available as a service. So we don't have to install the platform on a computer and make that computer accessible to the network. This is all done for us. And of course, since platform developers focus only on the platform and not on any specific application, they have the opportunity to do a very good job in that, and that will probably be a better job than what we would do if we had to address some aspect of a web application ourselves. So what about the business logic? We talked about presentation, we talked about data. Can we define business logic? Well, to define business logic, like the other aspects, we need a matching platform. If our application is a blog or a wiki, there may be platforms out there we can customize to suit our needs. But in the general case, for a general application, such platforms are hard to find. And at the absence of such platforms, developers resort to using a web framework. Now, a web framework is not a platform. It's not a complete piece of software. It's a partial piece of software. It's a partial application. It's a web application with holes in it where we are expected to put our implementation, like a model, a view, a controller sometimes, depending on the nature of this framework. But although these pieces of implementation are smaller and easier, this is still an implementation. So this is not what we're looking for here. What we are looking for is a platform, and our platform is called FishTank, that takes static files and can serve them over the internet, that can take data corresponding to a schema and support efficient storage and retrieval, and in addition can take logic and apply it to the data. And I'm not talking about imperative code that executes logic. I'm talking about actual logic, first order logic. So in today's demo, we're going to build a small microblogging application inspired by Twitter called Splasher. It has a very simple data model. It has two entities. One is A follows B, where both A and B are users, and the other is X tweeted Y at time T, where X is a user, Y is a string, the text of the tweet, and T is a numeric timestamp. We will define the business logic in terms of the output. In this case, we have the timeline. So the timeline for user U contains an event of the form X tweeted Y if U follows X and X tweeted Y. So what are we going to do today? We're going to define Splasher. We're going to define a schema, which is a set of typed signatures. We're going to define its logic by using first order logic rules, and define its user interface using HTML with directives. What are we going to use in order to do that? We're going to use FishTank, which is our platform. We're going to use a programming language named Cedalion, which is a programming language designed for DSLs, domain-specific languages. So in Cedalion, everything is a language. And it most notably uses projectional editing as the way to edit code. We're going to see what that means in a few minutes. We're also going to use a domain-specific language called Cloudlog. That is a data language, kind of inspired by Datalog, but Cloudlog is what we call a no data log language. It's designed for the NoSQL era, and it is embedded inside Cedalion. So we're not going to see a strict border of when we are in Cedalion land and when we are in Cloudlog land. Actually, those two languages share a website called Cedalion. You're welcome to visit it, of course. For the client side, we're going to use Angular.js and a Cloudlog plugin that is going to make our life easier when dealing with Cloudlog. So, off to the demo. So the first thing I want to show you is at least the logs from the FishTank server itself. It runs on Cedalion, and it runs on Docker, and it has the Cloudlog container is where the actual logic is, and it has a MongoDB instance as the database. And for this demo, I'm going to use this directory where I have a few HTML file and this directory with dependencies. Now I'm going to remove a file, and you'll see I have a script synchronizing content from my directory to FishTank. So you see all this data going up, and when we go to static HTML, index HTML, you're going to see this welcome page. Now let's look at the code. So index.html has, well, imports some JavaScript. It has Angular.js, Angular.js and the CloudLook plugin. And here there are some configurations. So the name of the application, the default URI, which is the welcome page, which it redirected us to. That welcome page is mapped to welcome.html. You can see it here. It has a header with saying welcome to Splash. And down here there is an ng view. That's a directive for Angular to say that everything that comes from this, the content of this page is going to actually be displayed inside this div. So this is what you see here. Now let's add a login page to our application. Now it's going to be a very simple login page. We're not going to authenticate anyone. We're just going to ask a user for their users for their names. So this is an input box. It is modeled. This is the Angular way to attach a variable to an input. So the variable is a session variable called user. The session itself is preserved when we navigate from one page to another. So we ask the user for the names and we navigate to the timeline location. Let's define the timeline location. It corresponds to timeline.html, and timeline.html at this point is going to have this header saying, repeating the name of the user and saying that this is the timeline. So let's see this in action. So I am Boaz, and we navigate to Boaz's timeline. Now let's move ahead to defining the data model. So we have two entities. I want to define them. So we are going to use Cedalion in order to define them. So Cedalion runs basically over Eclipse. This is Eclipse, and I have a project. We'll open it in 1 second. Called Splasher that currently has only this export file, which will allow us to later export the content of our Cedalion program and load it as logic to the platform. Now I told you that Cedalion uses projectional editing. Now it's a good chance to see what that means. Splasher. I'm creating a file called splasher.cd, and this file is a Cedalion source file. It's not your everyday. It doesn't look like your everyday source file. This doesn't look like your everyday source editor. It's a projectional editor. So what I'm editing is actually the abstract syntax tree of my code. My cursor is a rectangle that wraps around a node in that tree. In this text box, I can write some code. I can write some things, and when I press enter, they are projected in this part of the page. What I'm going to do is I'm going to create a sandbox. A sandbox is like a comment. It's a place for me to write code that doesn't have effect. And what I'm going to do is create an axiom, and so all my data as well as the rules are all axioms. So it's an axiom called follows A, B, meaning A follows B. Let's declare it. So A is a user and B is also a user. Cedalion doesn't know what a user is, so let's tell it it's a type. And now the cool thing about Cedalion is that you can give things your own projection. So you want follows AB to actually be projected as A follows B. And this is what you get here. Now I want users to be strings, like Alice. And that gives me an error because I wrote a string and it expected a user. So I'm going to wrap this with the word user and define user with the name to be user when the name is a string. And I'm going to give it a projection that would agree with how it is projected in Twitter with an @ sign. And also I'm going to make this an adapter, which means that it will automatically use this to resolve type errors. For example, if I write here Bob as a string, it will automatically add the @ sign next to it. So this is the following relationship. Let's add another sandbox and define yet another axiom called tweeted x, y, t, and basically follow the same process. So x is a user, the y is a string, and t is a number. Let's also create a projection. So x tweeted y at time t, and then we have something that looks exactly like this. Cool. So now that we have our data model, we can allow users to actually tweet. So we do this from this form. We have an input box that is modeled, that edits the text of the tweet, and we have this CloudLog directive contributed by the CloudLog plugin that associates the contents of this form with an actual fact that is going to, or an axiom that is going to be stored in the database. So the pattern of this fact is tweeted with user named user, which we get from the session, some text that we get from this input box, and the time that we get from calling a function now that returns the current timestamp. We call this fact a tweet, and when we click the submit button or press enter, it will call the function add tweet, which will add an instance of this fact to the database. By the way, this s colon thing is defined here as a namespace. So the namespace splasher in Cedalion, which is associated with the splasher project here, is given the alias s. We were at the timeline. Yeah. So let's see this in action. So, hi, I'm Boaz, and it was tweeted. Similarly, we can have a form for following other users. So here, so I'm going back to the welcome screen, and I'm using the fact that it does not authenticate, so I will use David's name, and I will follow myself. And right now nothing happens because we haven't defined the business logic yet. So our business logic is defined in terms of the timeline. So let's define the behavior of a timeline. So we can use behavior-driven development in Cedalion. We try to do it as much as we can. And let's define the behavior of a cloud log predicate. So the behavior, we want to define a timeline of user U with some event E and some time T. So U is a user, E is an event, which is a new thing, and time is a number, T is a number, and let's give it a projection similar to the specifications. So we want it to say is in, so E is in use timeline at time T. So now it looks like what we want, and we want to also do something. So it should provide all tweets made by followed users. So this is a behavior. We have a textual representation of the behavior, and here we can add an actual goal or actual test that will validate this claim. So we're going to use with simulate, and here we can put this is our place to put test data, and here we will put something that we want to be true. So our test data will be that Alice follows Bob, and that Bob tweeted hello at time 100. Now what do we want true? We want it to say that we want the timeline of, so we want some event to be in Alice's timeline at some time T. And that already is not true. This test fails. It fails because we haven't defined the meaning of the timeline. So we're going to do this using an axiom. And that axiom is simply going to be this. So something is in someone's timeline at some time. And this means unconditionally. So without condition, something is in someone's timeline. This is very general, but it is enough for this test to pass. Of course, this is not what we want. We want to also assert that E, which is an event, is equal tweeted xy with a certain values for x and y. Sorry. So x is a user and y is a string, and we are also going to make it look like the specifications, saying X tweeted Y. And in our particular example, X is Bob and Y is hello. And this test fails because we haven't assigned it any. We have a result, but we didn't give it any value. So what we are going to do is to make this axiom actually be based on some actual tweet. So we are going to turn it into a rule. So our rule says that if user X tweeted Y at time t, then X tweeted Y is in some user use timeline at time t. Let's save it, and the test passes. So it does somewhat we want, but it doesn't do all of it, because now every user has the same timeline and it contains all the tweets in the world, and that's not what we want. So we want another similar test that will say that it should not provide any tweets not made by followed users. And to test for that, we're going to ask for Charlie's timeline, and we're going to want that it will not have anything in it. So we're doing a not over that, and that fails because we do have a result. We get Bob's tweet. So here we will. So here we're going to make this conditional again. This time on the following relationship. So if U follows X, only then use the tweets made by X for use timeline. And that works. And this is actually all that we need. So we can go to this export page and export the content, and then we can go here and pull the image file created by the export and put it in our directory to be picked up by FishTank. What's left for us to do is to create the user interface. So this list will list the timeline entries. We are using the CloudLog query directive, which allows us to create to define a goal, a timeline in this case. User me is the user from the session, and it looks for events of the form tweeted, some user we call the author, in some text and some time. Now this ng repeat directive is an Angular.js and we call this thing the timeline. So it's going to go to a list that represent the timeline. So this list item is going to be repeated for every event in the list timeline, ordered by the time of the event in descending order. And for each element, we're going to show the author and the text. Let's see if it works. Yes, it does. So now David's timeline has one tweet made by Boaz. If I return to my page and make another tweet, and back to David's page, now you can see that these two tweets are ordered in the same order. Okay, fair enough. One thing to note about this implementation is the similarity. These are the specifications we started off with, and this is the code that we ended up with. Now, up to the order between those things, these are very similar. Now, it's no coincidence. We made sure to make them similar when we defined the projections for each and every one of them. So projectional editing helps us with that. But there is something more fundamental here, and that's the fact that these things are two of the same. These are two kinds of definitions of the business logic, and none of them is an actual implementation of the business logic. The difference is that while this was meant for people to understand, this one was meant for a platform to understand. So one question you may ask at this point is, yeah, but does it scale? Like, you managed to run this application without crashing, having 2 users and 2 tweets, but can you run it with say 1 million users and 1 billion tweets? So I cannot answer about this particular implementation. I haven't tested it in such a large scale, but I can tell you that the approach will work much better than many existing approaches. The reason is sharding. So in this particular example, I used one instance of a database running on my computer with one table, or in this case, a collection for holding the tweets. But if you do it in a large scale, like if you do it for millions of users, you will probably not be able to handle everything from a single computer, and you'll have to shard, to separate information regarding different users into different computer nodes. Now, you can either do it yourself using an SQL database, multiple instances of SQL databases, or you can use, like what I do, one no SQL database that shards for you, but you'll have to do it either way, or one way or another. So when in this naive approach, when we have a separate table for tweets that is sharded across different machines, when we want to make a timeline query, for example, we need to gather information that resides in different machines. So the timeline for a single user comes from multiple users that resides on multiple machines, and that is awfully inefficient. So what a lot of applications do is something called denormalization. They have an extra table on each node that holds the timeline information in our example. So when a user updates their timeline, their tweets, for example, writes a new tweet, the business logic goes ahead and distributes this tweet across many timelines, all their followers' timelines. So when a user wants to make a query, this is a simple query from a single table. How is it implemented? So when a user tweets, the business logic goes over all the followers that user has and puts the tweet in their timelines. But that's not enough. When a user starts following another user, the business logic needs to go through all the tweets already made by that user and put them in the first user's timeline. But that too is not enough, because deletion and probably modification needs to be handled as well. And now this looks all very symmetric and nice, but actually these things happen in different places in the workflow, so this is not this is typically far from trivial. FishTank is a platform that scales, pun intended. So it uses, as I said, an NoSQL database, in this case MongoDB, that charts for you. But this is not the important part here. The important part is that it denormalizes for you. Let me show you how it's done. So we think about facts and rules, the different kind of axioms that we have, like fish in a fish tank. So a rule is a female fish, like this code that we wrote. Now, when a male goes into the fish tank, a male that matches the left-hand side of our female, they fall in love and produce a child, which in this case is also a rule that matches Bob's tweets to Alice's timeline. And when that female meets a matching male, a tweet made by Bob, in the fish tank, they also fall in love and create this genderless fish called a clause that is an actual result. Now, if one of the fish is removed, all its descendants are removed, and which is what we expect. The order of insertion doesn't matter, so we can put this fish first and then this first fish, and the result will be the same. We can also put our data first and only then add the logic or modify the logic, and the result will be the same. Now this is something that is very hard to do in traditional systems. This process of changing the code after you already have data is called data migration, and it's a very powerful and painful process usually. Now let's try to do some searching. So we want to add a search box to our index.html. So this is this little form that asks the user for a search string and navigates to search, giving the search string as parameter, and that gives us search.html, which at this point will have a header which repeats the search string. Let's try it. Okay, so I'm looking for hi, and I'm getting no result because we haven't defined the semantics yet. So let's define the business logic. Search.cd, a new Cedalion file. I'll start with the behavior, and and this is going to be a predicate, a cloud log predicate, and it's going to be called search with a keyword and an event. Let's declare it. So this is a string and this is an event. I'm not bothering with custom projection here, so this is quite nice. Now it should provide all tweets containing a keyword. And the test is going to be, so I'm going to give it one tweet. So Alice tweeted 1, 2, 3 at time 100, and I want to simulate a search of for 2, and I want to receive some event, and that doesn't happen because we haven't defined search yet. So this is also going to be an axiom and search, and I'm just saving it, and it passes. But this is still not going to give me a variable, a good result. So I'm adding an assertion. So I want E, which is an event, to be equal tweeted. So we want Alice tweeted this thing here, and we're getting a, and this doesn't happen. So this is our keyword, and this is our event is some X tweeted Y, and we want that to be conditional on an actual tweet. X tweeted Y. Test passes, but we're still ignoring the keyword. So let's add a test that will not allow us to ignore it. So it should not provide any tweets not containing keyword. So let's search for and ask that to fail. So we want that not have any result, and it fails. It does have a result. So there are two ways to actually handle this. One is to add to here the requirement that Y contains keyword, but that will be bad from a performance point of view, because this rule is going to create one of these for every tweet. So if I want to filter out the ones that, so this will actually filter out, go through all my billion tweets and filter out those that do not have the keyword. That's not what I want to do. What I want to do is create something like an index. What I want to do is, on the left-hand side of this arrow, I want to first check that the keyword is indeed in Y, or generate a result for each keyword. So I do it through a guard. And in the guard, I'm going to use is a keyword. So KW is a keyword in Y. Now, is a keyword is a predicate that I prepared. It's a Cedalion predicate. You can look at its definition here. So there are a lot. You can see its projection, its step signature, projection definition, and of course, and its actual definition, semantic definition. But you can also see its spec, which says it should extract words in a text, it should ignore stop words, and it should ignore case. All things that we want. When I save it, you see that the test passes. Let me export it again. And import it again to here. Now let's open the place for the results. So this is again a cloud log query with a list containing the results, and let's see if it works. Yeah, it works. I search for hi, I get hi. It works. Looks like it works. Okay, wrapping up. So, development status. FishTank is still a proof of concept. It's not something you can use in production or in other capacities. There are a lot of features missing. There is a big performance gap between where we are and where we want to be. But to conclude, in order to define your application, you need a platform. And FishTank is a universal platform for web applications. You define applications using logic rules. These logic rules typically resemble their specifications. And these rules allow you to denormalize data, which is something you need to do if you want your application to scale. Thank you very much.